Good day, grade 10th. Today we're going to be looking at the effects of center of mass. Yes, it's me, it's Marshall A.C. Candiado. We just want to do this, it's just going to be, I hope it's going to be a quick video because we already discussed most of the stuff in relation to center of mass, and we just want to continue looking at how the center of mass has effects on different bodies depending on the shape of the body, depending on the size of the body. Then what's also important in this lesson will be the aspect of how you can find the center of mass for an irregularly shaped object. Because you'll find that for objects that have regular geometrical shapes, the center of mass is usually easy to determine. But for irregularly shaped objects, we'll see in this lesson how we get to determine that the center of mass for such an object. Okay, so the objectives by the end of this lesson, we must be able to describe the effect of center of mass on the stability of an object, state types of equilibrium, describe an experiment, determine the center of mass of an object. So those are our objectives for this lesson. So just look at the objectives and get ready for the lesson. Okay, so on the screen right now, we're looking at a concept of toppling force versus stability. To say, if an object was to tilt at a certain angle, at which angle would it be able to go back into its normal position, where we would say it is stable, or to a position where you could say it's now going to topple over or fall over. In the previous lesson, I remember we had an image, a diagram of a double-decker bus where it was being tested to see if at the angle of 28 degrees it would still be able to continue and go back to its stable position, or if it would topple over at an angle if it is tilted at an angle of 28 degrees. So what you see in the different diagrams, I'm sure you can read. You can read there it says diagram A, diagram B, and that's supposed to be diagram C. What we just get to see is that, okay, so initially the object, it's a, what do you call that shape? It's not a square, is it? It's a rectangle. Yeah, that shape is a rectangle. So because it's a rectangle, it's very easy for you to determine the center of mass for a rectangle because its geometrical center is its center of mass, right? We are assuming that this is a uniform object where the particles are distributed uniformly on this particular rectangle. So its geometrical center would be its center of mass. So if it's just tilted slightly, it goes back to its stable position. If it's tilted extra, as you can see in the case of B, right? In the case of B, you will find that even though it has been tilted, the center of mass has not exceeded the position to which you would say it's going to fall, right? So it will balance, and if it's actually at the center of mass there, it may actually remain in that position for a while, right? But sooner or later, it probably will go back to its normal position. But with diagram C, as we saw, right, you have exceeded, its weight is now towards the side where it topples over, right? Because the object will always move towards where there is a greater weight. So if there's a greater weight to the side where it will now topple over, it will topple over, right? If it's balanced like there on diagram B, the weight is distributed directly in the middle, so it might actually balance in that position, right? So we also have different objects, and I'm sure this is what we explained in the previous lesson, how you have, if something, in the previous lesson we mentioned how if something is shorter, it's more stable. If it's shorter, it means its center of mass is lower, therefore it's more stable. You also increase the stability of an object by giving it a wider base. By giving it a wider base. So you'll find that, that's why we say if you spread your legs, right, if you're standing and you have a wide anchor, right, you're not having your legs firmly to each other, there you don't have that stability as compared to an individual who has put their legs a certain distance apart. Okay, so you can see here with the tripod, there's a tripod, there's a fan, but all of them have been given a wide base. Imagine that fan not having that wide base. Would you be able to have it stand on the ground? No, it would just fall over. It would fall over. So when we talk about types of equilibrium, right, I'm just flowing through this. Why am I doing this? Because in my mind, I am of the assumption that this is simple material, which we have covered. But if you still need a bit of time, you can pause the video, look at the chair, the fan, the tripod stand. I have no idea what that wooden thing is. You'll probably tell me what that is. Just look at them and get to see how their stability is increased. Okay, so now let's look at the types of equilibrium. And we have three states or three types of equilibrium. We have a stable equilibrium, we have an unstable equilibrium, and we have a neutral equilibrium. Those are the three types of equilibrium. And from the description that is given there, we have an image of a coin, right? We have three coins that have been placed in three different positions. The three different positions representing the three different types of equilibrium. So if something is in a stable equilibrium, look at that coin. I'm sure you have seen coins before, right? If a coin is sitting like that, it's very likely that if you disturb it, right, it may just tilt and then it goes back into its original position, depending on how much you displace it. If you push it too much, obviously it's going to topple over and it's going to fall. But we're saying if it's displaced slightly, it's just going to tilt to the side, but its weight will cause it to go back to its original position. And we say that object is in a stable equilibrium. And don't limit this to the cone that's on the screen. Think of it in terms of different objects. Think of it in terms of a car. Think of it in terms of a bus. Think of it in terms of any object, in terms of an individual, to say, if I was to tilt this much, and then would I just go back? Just imagine if you're standing there, you're walking towards Metuliki to get your food, then someone comes and bumps into you. If you don't have a stable equilibrium, right, you're most likely going just to fall over like a pile of bricks, right? But because you have a stable equilibrium, you may just deflect just a bit, you get back into position and you say, dude, what are you doing, right? So think of it, open up your mind and think of it in terms of different objects and different scenarios. But then if you look at the object that is in unstable equilibrium, just think of you, usually we stand on our legs. Just think of you if you're in an inverted position and you were using, that thing where you put your arms on the ground and then your arms are in the and then your legs are in the air. That's a very unstable position, right? So in the same situation, just imagine if you're standing in an upright position and I come and I push Maria, right? She's just going to move back a bit, right? But if she's on her hands, what do you call those things? Like those things that you do. Maria, I don't know if you do those things in judo, in taekwondo, right? Where you stand on your arms. But if someone pushes you, right, your stability is very low. Your stability is very low, so you're going to fall over, right? And it's going to be difficult for you to then naturally go back into that position, right? Worse off with Mr. Korn over there. There is no way that Korn is going to go back into that position, right? So if it's displayed slightly, it's going to fall over and it can't go back its natural position, which is effectively an unnatural position anyway. If we talk about a neutral equilibrium, now imagine you're laying on the ground. You're now laying on the ground. It doesn't matter if we push you or if anything, if there's a deflection, because you are already lying on the ground. So which means that your center of mass is so low. Your center of mass is so low that there is no way you can topple over. How do you topple over? You're already on the ground. So your center of mass, so always relate these things in relation also to center of mass. Right. Key aspect of this lesson, this one. Let me just play this video, which will hopefully explain the concept of finding the center of gravity for an irregular shaped object or lamina. Right? I don't know why it says car there. Irregular shaped car. What's an irregular shape? Let's just say irregular shaped object, not car. Let's say irregular shaped object or lamina. Okay, let's just play this video.
Gravity. Only one point on which the cardboard can be balanced. This point where the cardboard can be balanced is called the center of gravity of the cardboard. Thus, the center of gravity is the point through which the resultant of the weight of all the particles of the body acts. Let us now determine the center of gravity of an irregularly shaped lamina using a plumb line. Make 3 holes near the edge of the lamina so that the lamina can swing freely when pivoted from each hole. Suspend the lamina from the point P as shown here. Hang a plumb line from the point P and mark the plumbing line P' on the lamina. Repeat the experiment by suspending the lamina from Q and mark the plumbing line Q'. Now follow the same procedure for the point R. We observe that all the 3 lines PP', QQ', and RR' intersect at one point. This point where all the 3 lines meet gives the center of gravity of the lamina.
Okay, so if we are looking at that, so we're saying what you have to do is you have to put 3 holes on whatever irregularly shaped object that you're going to have, right? And you're going to just hang that lamina. We call it lamina. This is physics, yes? We call it lamina. You just hang that irregularly shaped object on your rotor stand. That's a stand. You just hang it there, and then you place a plumb line. Is just if you've ever seen a pendulum ball, right? It's usually there's a string. We just put a pendulum ball or a plumb line, and we just let it hang there. And we draw a line, a continuous line, as was being shown here. We just draw a continuous line that follows the plumb line, right? That follows the plumb line, or if it's a pendulum ball that we're using. So you hang it at all the 3 different points. You have just put 3 different holes, 3 holes on whichever object that you have on your lamina, because it's not regularly shaped, so its geometrical center won't be the center of mass. So you can only determine the center of gravity or the center of mass by following this procedure. This procedure is given here to say procedures of determining the center of gravity or mass of an unshaped card or unshaped lamina. So make sure that you go through this process, because it's important for you to be able to describe how you can determine the center of mass of an irregularly shaped object. So what I want you guys to do is to just, you play the video again when we've finished this WhatsApp lesson. Then you just go over the material from the first lesson, center of mass. You try to just get a basic understanding. These are simple concepts, but my fear for you guys, because myself, I have no fears, but what I fear for you is that you take simple things as though they are too simple and then fail to recall those simple things. You try to focus on difficult things and still fail the difficult things as well. So give your utmost attention to every concept that we do, right? So what I always say, that always do your best. Always do your best. Your best will differ from time to time depending on how hungry or how full you are or how happy or how sad you are. But what's important is that for every concept that we do, you give your utmost best. That's all I ask from you guys. So thank you very much for watching this video, right? Thank you very much. I'll meet you guys tomorrow in